Hello students, in this video we are going to learn about JK flip-flop. Previous video we saw about the implementation of SR latch by using static CMOS design. So here we will be learning about flip-flop, and now the first flip-flop that we are going to learn is JK flip-flop. So what was S and R stands for in previous latch? Just set and reset. And now J and K is used to honor the scientist who discovered it, Jack Kilby. So here, what is a flip-flop? Flip-flop is a memory storage device, whereas it is an edge-sensitive device. What is it? It is an edge-sensitive device. Your output will undergo a transition during the rising edge or during the falling edge. How can I construct a flip-flop? If I combine various latches, I can get flip-flop. So the building block of flip-flop is nothing but latches. So first, whenever we want to design a flip-flop, we must first know how to implement the particular latch. If I know the implementation of latch, I can easily design a flip-flop. So what is this JK flip-flop first block diagram? It is J and K, which are the inputs. Q and Q bar are your output, and E, which is the enable pin. Now, I'm drawing the gate level implementation of your JK flip-flop. What is it? We have 4 NAND gates, and the inputs are clock as well as J, and the output of the second NAND gate is given as the input of the first stage. In the same way, Q is given as the input to the first NAND gate. So, how many NAND gates are there? 4. So, previously we saw if we have NAND gates, you can just write how many NAND gates are there, what are the inputs of the NAND gate, what are the outputs of the NAND gate, and directly provide the namings. Directly provide the namings that will give you the JK latch. Now I'm going to implement a flip-flop. So I have to construct 2 latches, and one input will be the normal clock, and enable pin of the second latch will be the inverted clock. Right? So first is J1, K1, Q1, Q1 bar are belonging to the first latch, and the second latch is J2, K2, enable to Q2 and Q2 bar. Now, I am giving a clock signal as it is my flip-flop. So, this clock signal is given to the enable pin of the clock signal is given to the enable pin of the first latch, and the output, which is the inverted clock, which will be given to enable 2 of your second latch. So, this is nothing but your JK flip-flop. I have constructed a JK flip-flop just by combining 2 latches. Is it clear? Now, we know all these things. These are the gate level implementation and the block diagrams, everything. Now, how can I implement the same using CMOS logic? How many NAND gates are there? There are 4 NAND gates. So, easily you can give the numbering as 1, 2, 3, and 4. And how many? You just write NAND 1. What are the inputs? What are the outputs? NAND 2. What are the inputs? What are the outputs? NAND 3. What are the inputs? What are the outputs? And just draw the pull-up network, pull-down network for all the NAND gates and give the namings. Right? But now we have 2 latches. So how many number of transistors we require? We require 8 transistors, 8 NAND gates added with a static inverter for inverting your clock. So this is highly a complex process of drawing. If suppose you don't know in your examination, if you get some question, implement a JK flip-flop using CMOS logic. If you don't know how to draw using any other logic, easily, blindly you can attempt that question by writing the answer for static CMOS logic by connecting a pull-up network and a pull-down network. Now, I'm using excitation table. I'm going to show you how I can implement a JK flip-flop in an easy manner without taking that much of risk. Right? So what is this excitation table stating? Qn being a present input, and J and K or the inputs. So Qn, J and K being the input, Qn plus 1 be the output. So now there are three inputs named as Qn, J and K. For three combination, I can have nearly 8 variation in your input 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1. So now for these, what is the next state output? It will be 0, 0, 1, 1, 1, 1, 0 and 0. Right? If my present past state is 1, but whereas my reset J, nothing is but reset. When your reset is 1, I am giving my output as 0. So now this is the excitation table you know previously for a JK flip-flop. But analyze from the table what is given. Whenever your Qn is equal to 0, the next state Qn plus 1 is nothing but your J. See the J value and see the Qn plus 1 value. Whenever your Qn is equal to 0, whenever my Qn is equal to 0, the first four things, whenever my Qn is equal to 0, my next state is nothing but 0, 0, 1, 1. What is this 0, 0, 1, 1? It is same as J 0, 0, 1, 1. Whenever my Qn is equal to 1, whenever my Qn is equal to 1, my next state is nothing but wherever K is there, I'm having the complemented version of K. So 0, 1, 1, 0, 0, 1, 1, 0. So from the table, I analyze certain things. Now what I can do? I can keep Qn as my control signal and I can pass a data. What data I can pass? I can pass J and K bar. So when my Qn is equal to 0, I have to pass J. Whenever my Qn is equal to 1, I have to pass K bar. So what is this? Is nothing but a 2:1 multiplexer. So now my 2:1 multiplexer is going to function like a JK flip-flop provided my data input are J and K bar and my select line is Qn by using transmission gate. So see for the top transmission gate, I'm giving Qn is equal to 0. I'm giving Qn is equal to 0. My top transmission gate is turning off. Qn bar becomes equal to 1 and that 1 is going to turn on the bottom transmission gate. See, I have just drawn NMOS. You have to draw a parallel PMOS to make that as a transmission gate. It is not a pass transistor. We have to connect a PMOS and you have to make it as a transmission gate, right? So now when Qn is equal to 1, my Qn bar will be equal to 0. So what will happen? 0 will turn off the bottom transmission gate, whereas it will turn on your top transmission gate, thereby passing K bar. So my output will be having either J or K bar, but after some time my output is going to discharge. To prevent the leakage, I am using a D flip-flop that is going to act as a buffer. So whatever my input is there, that will be stored in your output and there will not be any charge leakage. We shall see what actually is a D flip-flop, how it is acting as a buffer in our next video. So in this video, we just saw about the implementation of JK flip-flop by using two JK latches. You can directly use a static CMOS that I have shown in the previous video, but instead I am just using the excitation table. I have analyzed the excitation table, how excitation table is working or how my JK flip-flop is working by using Qn as a select line and J and K bar be the inputs, so that it's easy to simplify the diagram. And see here, I have to connect a PMOS in parallel that is not drawn over here, and that will be giving you the output of a JK flip-flop. So in next video, we shall see about D flip-flop. Thank you.